will present the results and achievement of ARLISS 2024. And afterwards, we would like to decide this year's ARLISS Awards. This will be the program for this meeting. First, I will explain about this meeting. Meeting program, kind of awards, and the presentation order, and how to vote. After this explanation, we will start the presentation in order. Because of the large number of teams, we will divide the teams first half and the second half. There will be a 5-minute break after the first half of the team's presentations. After the presentations by the participating teams, the management teams will make a presentation about the concept. And after that, UNISEC Faculty Professor Inamori will give us remarks. And after 15 minutes break, we will present awards for ARLISS 2024. Okay, I will explain kind of awards for ARLISS 2024. This year's ARLISS has 6 awards. The Accuracy Award, only combat competition participant can win this award. This award will be given to the team that comes closest to the goal. We decided from 1st to 3rd place. Next, Best Mission Award. This award is determined by the number of points obtained through audience voting. And the evaluation criteria are mission superiority, mission feasibility, and mission uniqueness. We decided from 1st to 3rd place. And next, Technical System Award. This award is determined by the number of points obtained through audience voting too. The evaluation criteria are technical novelty of the system and the technical difficulty of the system. I will decide from 1st to 3rd place too. And next, overall winner. This award will be given to the team with the highest average value of Best Mission Award score and Technical System Award score. We decide one team only. That means this award is MVP of ARLISS 2024. Next, UNISEC Award. This award given to the team selected by UNISEC Faculty. We decide one team only. And the Challenger Award. This award is only the team that challenged the new type goal can be selected for this award. This award given to the team selected by ARLISS management team. We decide one team only. Okay, this is the award for ARLISS 2024. Okay, I will explain how to vote for each award. Please scan this QR code. This is the form. Please choose one representative for each team and make sure that he or she answer voting form. Only one representative for each team. And please enter the scores for each team as you listen to the presentation. And please answer the following items on a 10-point scale. Best mission. For best mission, mission superiority, mission feasibility, and mission uniqueness. For technical system, technical novelty of the system and technical difficulty of the system. And please score 10 points for all items to your own team. If you answer your own team, please score 10 points. Okay. And if there are participants who is not participating in this meeting, please score 1 point to this team. Okay. Okay. Oh, sorry. Okay. Then this is the presentation order for this meeting. This year, 90 teams participated. And the first half of the teams, teams number 1 to number 10. And the second half of the teams, number 11 to 19, number 19. Okay, now I would like to move on to the presentation. The first team is Tokyo University of Information Science Supernova. Please prepare your presentation.
Okay.
Mm,
Can you see?
Sorry, I can see your slide.
Okay.
Mm,
Can you see my presentation?
Yes.
Okay. Let's start my presentation. Hi, we are Tokyo University of Information Sciences, Supernova. Let's start my presentation. I'll show you the features of CanSat. The mission is to reach the limit goal using object detection with deep learning and TOS distance information. Object detection uses AI to detect objects in square areas. Model is MobileNet SSDV2. And multi-zone TOS can take distance 8 times 8 multi-zone. It can run guided to 0 meter while measuring the actual distance. Goal recognition images are shown on the right. Goal is recognized by light blue square area in object detection, and a lot of numbers are displayed. This is the distance measuring by TOS 8 times 8 in 64 locations. Accurate 0 meter goal with object detection and distance measurement. Now let's move on to the ARLISS results. I'll explain the results of the first plot. Here is the result in photos. The CanSat fell 8 km east and got stuck in the large grassy area. Next are results of the second flight. I'll explain the result of the second launch. Here is the result in video. CanSat landed 3.8 km from the goal, and CanSat successfully separated from parachute. CanSat runs straight to the goal by GPS. CanSat reaches near the goal. And CanSat started goal recognition with object detection and TOF measurement distance. CanSat achieved 0-meter goal. Image log is on the left. CanSat detected the goal with object detection and achieved 0-meter goal while measuring the distance of the goal with TOF. And CanSat detected the distance of 10 centimeters and judged the goal at 0 meter. The right figure shows the running path. CanSat ran from 3.8 kilometers to 0-meter goal. Driving time was about 1.5 hours. Finally, I'll show you the results of my success criteria. Mission was full success. Equals to success was a partial achievement. That's all. Thank you, ARLISS official, and thank you, Airpacks. And thank you, all ARLISS members. Thank you for listening my presentation.
Thank you very much for your presentation, Supernova.
Thank you.
Okay. Next team, Niigata University NICS OverLights. Please prepare your presentation.
Okay. Can you see the PowerPoints, right?
Yeah, I can see your slide.
Thank you. Okay, we will now present the results of ARLISS 2024 from Niigata University. I'm Ryuta Sorimachi, the project manager of our projects. Okay, these are contents of my presentation. First of all, I introduce our teams. Okay, the team name is OverLights and consists of 7 members. And our mission statement is demonstration of 0-meter goal by a concept with more reliable startup performance and longer time operation. Okay, next, about our concept. Our concept has 2 features. First, it's robustness. We use high retire of GFRP, glass fiber reinforced plastic, and TPU, and we use carrier to start driving, and it's very reliable. And another other feature is its endurance. We use 2 types of computers. One is Raspberry Pi Pico for driving to go, and other is computer module 4, Raspberry Pi computer module 4 for using camera. And we can make it lower power consumption and longer battery life. And next, about our mission. Here is our success criteria. minimum is start driving without damage. The full success is achieve the main goal. And extra success is the total distance of this contents meets the over 6 kilometers. And we determined this data from past data of ARLISS. Okay, next about results and considerations. First, we succeeded to the main goal on first launch and first ARLISS. Okay, I explain details. We can't sorry. And the minimum success is succeeded, and of course also for success is succeeded. Here's a video from camera on the CanSat. And next about extra success. The landing point is 3.3 kilometers from goal. And from the control record, the remaining distance can be driven. It's 0.56 kilometers. So about extra success, we failed. About considerations, actually on the way to the goal, the CanSat was being stuck about for 15 minutes. So we think that it consumed a significant amount of power by being stuck for 15 minutes. And here is the comparison of the wrong time operation test and fast launch. You can see it's very different. Okay, next about result of second launch. We failed to detect landing and retired. So all success criteria are failed. Next about consideration. We use aluminum rod on the CanSat, but it was broken. But the parachute was not broken. And from the control record, the terminal velocity was about 6 meters per second. So we think that the rocket separation load was more than expected. And about consideration, we determined that conditions for landing detection, that altitude meets over 100 meters. But for the program restarted by more than expected growth. So the altitude diameter resets again. So we failed to meet this condition. So we failed to detect landing. And last contents about lesson and learned. First, the assumption about ARLISS environment was insufficient. About, for example, being stuck, and also other parts was broken. So we needed to review the test contents. And next, with the cooperation of many people, we will be able to achieve results. So in the last, we sincerely appreciate everyone's cooperation with ARLISS 2024. Okay, that's all my presentation. Thank you for attention.
Thank you very much for your presentation. And the next team is Shibaura Institute of Technology SHARXS, Astrum. Please prepare for your presentation.
Okay. You can see this, my presentation.
Yes, I can see your slide.
Okay. So let's start. Let us begin with a presentation from Astrum, a team from SHARXS at Shibaura Institute of Technology. Table of contents. First of all, let me explain about SHARXS. This is our second time participating as SHARXS since 2018. We lost technology in COVID-19. However, we are back here again. We have only 4 team members, but we set a goal of zero distance goal. Our mission statement. Our mission is to achieve the zero distance goal. To achieve this goal, we have set the following 3 small goals. About mission details. Mission details are the same as in the rubric, so I skip them. About success criteria. We have set the zero distance goal as advanced success and the smaller goals indicated in the mission statement as full success and small success. Evaluation method are visual inspection and from logs. About our machine. Based on the machine that participated in the Tanegashima rocket contest, we worked on the machine in the form of brush up the point to be improved. Tire materials have been changed to increase impact resistance, and the battery capacity has been increased. It also used the shaft structure shown in the figure to increase impact resistance. The software uses Euro V8 as a model for object detection, enabling fast and accurate detection with limited resources. In order to save time, we will omit this section. So next, I would like to explain the result of the competition. We had 3 launches, but as a result, we were not able to achieve success criteria. Let us explain the details. About first result, the program stopped due to an error when reading data via I2C. The machine did not operate and was retired. Some of the electrical components were also damaged. To improve them, we reinforced the electrical components and modified the program. Our second result, the connection between the parachute and the separation mechanism was turned off. The machine free falls and is wrecked. To improve them, we reinforce the connections. Our third result, we successfully made a soft landing by parachute. However, the impact of the landing causes the Raspberry Pi to reboot. To improve them, program should start even after rebooting. Finally, I would like to thank everyone involved with ARLISS and AirPack. This concludes my presentation. Thank you.
Thank you very much for your presentation. And if you for participants, if you don't have inconvenience, please turn on your camera and make a reaction to the presentation. Okay. Next team is Muroran Institute of Technology, SARD, SFIDA. Please prepare your presentation.
Can you see?
Yes, I can see your slide.
I'm going to start SFIDA's presentation. Our mission is collect data on the exploration route with CanSat achieve the 0-meter goal and acquire data to reflect on the surrounding map to understand the environment of the exploration route. Next, I'll explain the feature of our concept. First, transform tire. This expansion with approximately 1.5 times. Second, good maintainability body. This time, the body is equipped with a slide mechanics. Third, get a lot of data in addition to the minimum data necessary for CanSat. We also made it possible to acquire sound and vibration data. Next is about result. Our results shows that the parachute opened normally and the landing was successful. However, due to a programming error, it was unable to complete subsequent missions. So our mission accomplishment rate was 0%. We believe this is caused by the rocket's strong vibration. In the experiment, it was able to withstand vibration, so we would like to find out why the programmer's error occurred on investigate the limits of how much strong it can withstand. Thank you for listening.
Thank you very much for your presentation. Okay, the next team is Universidad Universidad Nacional de in Cosmics. Please prepare your presentation. Cosmics. Okay. I think that team is not here. So next team. Next team is Tokyo Metropolitan University, TMU NAVi. Please prepare your presentation.
Okay. Okay. Can you hear me?
Yes, I can hear your slides.
Okay. Let's start. Hello, I'm the project manager of TMU NAVi. We are a team of 4B4 students and worked so hard for this project this year. Now I'm going to explain about our rover NAVi. Okay. First, let's talk about the mission background. Traditional path planning method of CanSat mostly did not take into account threats or obstacles that may be present between the CanSat and the goal. This could lead to the CanSat being stuck, so this is the problem that should be taken care of. Next, let's look at how axial mass and lunar rovers do the path planning. As you can see, these rovers path plan using sensors as well as by the help of an operation team on the Earth. From this background, we came up with innovative mission. Our mission statement is demonstration of navigation using route planning based on satellite imagery. The defining aspect of this mission is that CanSat does the route planning autonomously. This is the mission sequence of NAVi. First, path planning based on satellite imagery. Second, navigation based on planned path. And guidance using image recognition and distance sensors. And finally, touch goal. Now I will talk about the tire of NAVi. NAVi's tire can absorb the impact from landing by incorporating a spring structure both along and horizontal to the tire's rotational axis. Additionally, grazers were added to achieve excellent runnability. As for image recognition, we use YOLO for cone detection. As you can see from this image, NAVi could detect the cone successfully with high accuracy. Most importantly, let's talk about path planning. We gained satellite imagery using Sentinel Hub. Upon landing, NAVi initially processes the image data and satellite images are processed sequentially through grayscale conversion, finalization, smoothing, and dilation. After that, NAVi implements a route planning algorithm to avoid topological obstacles. In this study, the A-star algorithm was employed for route planning. A-star is particularly effective in ensuring both reliable and efficient shortest path design. Finally, let's look at the final result of ARLISS2024. Our CanSat NAVi ended up free-falling. However, it managed to perform path planning after landing, as you can see from these images. From zoomed image, you can see that NAVi successfully managed to plan a path that avoids the obstacles that can be seen as white dots in this image. Although it was not possible for NAVi to touch the goal, we are glad that it managed to perform an innovative sequence. From ARLISS 2024, we learned these lessons. In the pursuit of system development, There is always room for improvement. Therefore, as many attempts as possible should be made, and all possible problems should be resolved. And the collaboration and knowledge sharing within the community can lead to collective growth and innovation. Therefore, experience should be shared as a heritage for the continuous enhancement of technology. Last but not least, thank you, AeroPack. Thank you, ARLISS management team, for making this opportunity possible. And thank you for listening. This was TMU NAVi. Thank you.
Thank you very much for your presentation. The next team is Tokyo Metropolitan University, TMU Super Spider Liner. Please prepare for your presentation. TMU Super Spider. Okay. I can see your slide.
Thank you. Can you hear me?
Yes.
Okay. Hello. We are team Super Spider right now. Okay. Our mission statement is verification of surveying techniques for the selection of construction plots for the lunar base. Mission items are surveying constructive area and marking construction area. Constructing requires exploring flat area that doesn't have bump-free area. In ARLISS, we designated enable construction area with ruts or hole where rover gets stuck. Marking is necessary for construction robots, etc. to use as a sign for construction. In ARLISS, our CanSats move to the four corners of the proposed construction area and place markers. To move to the destination, GNSS, cameras, etc. were used in ARLISS until now. But in reality, there is no GNSS, geomagnetic, or cone in the lunar environment. Therefore, our CanSats are divided into a parent and child, with parent controlling child by using string to move to destination. Parent acts as a base point and sends instruction to child without moving. Child moves and places markers as instructed by parent. From launch to landing, child stored in parent. After landing, parent deploy and child is released from parent. Our mission will flow as shown in the image. After parent is deployed and child is released, our CanSat search around parents to select a construction area. I explain releasing system. Parent fit with a text fuse with nichrome wire and parent deploy. To parent deploy, we use convex because convex is high deployment and light. We designed to stand upright after deployment, no matter which direction CanSat folds. Please look left movie and please look right movie. Parent successfully deployed. Please look right movie. child successfully released. Next sequence is search and place. Parent has volume. Please look like movie. Connect string to the movie parts of the volume, detect the direction of the child by changing the volume resistance value. Parent has encoder. Connect the encoder to the reel on which the string is wound. Measure the amount of string released by the rotation of the reel and detect the distance of the child. Parent can locate from distance and direction by using the two systems. Left figure is movement of child detect. Left figure is movement of child detected by the parent. Right photo after the mission. Marks where child has moved. Parent can operate on the mark. Parent can locate and operate the child. I explain stack detection system. Parent has motor. When running, it released string. When child is normal running, string is pulled tightly and motor cannot wind up. When child stuck string, I not pulled. When child stuck string, not pulled enough and motor can wind up. Motor winds at regular interval. Encoder check if it is wound up and detect stuck. Child stuck in hole.
Sorry, time is up, so please a little bit early, please.
String are running and parent is stuck. Parent retrieve child. Marking system, rotating plate and marker false. Child reach the destination corner. Place a marker. Left figure is coordinated by parent machine, parent log. Parent determines the coordinate of the planned placement. Child went to put markers on all four corners. Our mission completes the entire mission. Our CanSat completes the entire mission sequence. Our CanSat searches to a point geometer away from the parent with a go meter square as planned placement coordinate. Left figure, orange is planned placement coordinate. Blue is coordinate at which the parent recognize that the marker was placed. Green is coordinate where the child actually went to place the marker. Average of distance between the planned and actual coordinate is 60 centimeters. Our mission achieved within 1 meter distance was the full success factor. Review. Thank you for listening, and thanks Aeropack and ARLISS management.
Thank you very much for your presentation. Okay, next team is Tokyo Denki University TDU Space Project. Please prepare your presentation.
Can hear the
Sorry, Mr. Yamada. Please turn on share slide. Turn off, please. Thank you.
Okay, can you see it?
Yes, I can see.
Okay. Hello everyone. I would now like to begin the results presentation for TD Space Project ARLISS 2024. Okay. And the first, now let me the both our launch was 2 times threefold. Now I will now present the outcome and our reflection on this result. First, our mission is a quick scout CanSat for rapid exploration. After landing, our CanSat is after landing. Our CanSat will head straight to the goals, and it is very powerful CanSat, and that overcome all the rats and obstacles along the way. Okay. Our CanSat was featured with CFRP monocoque body and with 4-wheel drive systems. It's very it is very tough, and it can run very fast speed. This is the inside of our CanSat. 2 motors drives each side of wheels via center 2 propeller shafts. CanSat turns by controlled by the difference in the rotation speed between the left wheels and right wheels. For long-range navigation, we use GPS and 9-axis sensors. And for short-range navigation, we use cameras. It uses OverLights 2640 and ESP32. Okay, next, let me report our result of launch. In the first launch, there was error in calculating the pressure speed, which caused the descent speed to be 1 million times faster than expected. As a result, separation occurred very high altitude. It is about 1,200 meters and landing to freefall. Upon landing, the impact caused the wheel 4 wheels was broke, and some internal gears damaged, so it was repaired. However, the body and frames remained intact, and after replacing the wheels and drive shaft, the rover was ready for the second launch. In the second launch, it was freefall because as human errors, we use air pressure and time to judge the separation. For time setting was a mistake, so its separation was occurred 30 seconds after the judge of the descent. So result in the second free fall, the impact was more hard, so more than first. So our steel drive shaft was bended, and internal motor mount was broken. It broke battery, but internal circuit board inside was saved and saves the camera, and we can capture the image to we can capture the image for free falling.
Sorry, time is up, so please a little
Okay.
bit early, please.
Okay. Okay. Finally, I will address the achievement of our success criteria. We said the 4 success criteria are comeback performance and driving speed performance, straightness, and radio performance. We are preferred, so only radio performance minimum success was achieved, and all other success criteria it was missed. Okay, that's all. In conclusion, I would like to express the gratitude to everyone involved in ARLISS, and with that, thank you for listening.
Thank you very much for your presentation. Okay, next team is the University of Electro-communications, last Highball. Please prepare your presentation.
Can you hear me?
Yes,
Yeah.
I can see.
We are University of Electro-communications Japan, Takadama Lab, last Highball. First capabilities are necessary for rover. Likely, they are mobility and exploratory abilities. On the other hand, conventional rovers tend to be large and possess excellent traversability, but they have limitations in their exploration range. JAXA envisions multiple small rovers working in coordination as future rovers. However, they introduces challenges for mobility. Therefore, we propose as our mission portability rover that can combine and separate. Method. The steps for combining as follows. First, adjust the motor by rotating each side and detecting the rotation amount with 9-axis sensor.
we will find minimum motor power that allows stable movement. In second, detect the rover using YOLO and approaches the front of the air marker attached to the rover, or maneuver around the ensure that the face is visible, like this. In third, utilize posture of the air marker to approach it while tracing an arc. This theta and theta, so it's draw arc and like this orbital. In fourth, contact the face of the air marker with lateral deviation of the tires within 3 centimeters, like this. 5. In the fifth, combine using the combination sequence, like this. The flow of the mission is as follows. The first, aim for the old goal. Then combine in its density and head towards the new goal. Once reaching area near the new goal, separate and achieve the new goal. Our mission target is in this red area. Combine and move in 4WD and separate. The results were not favorite. In the first attempt, there was free fall, and in the second, we failed to separate parachute due to impact damage from the fall. However, during the brief of time before technology exchange meeting, we repaired the launch and conducted experiments, resulting in a successful combination. This suggests that if we fully address the countermeasures of the fall, the mission has chance of success. In summary, our purpose was mobility and exploration. Mission was combinable and separatable for the rover. Method is guidance with motor power adjustment and air markers. The result is free fall and parachute separating failed. In future, as the future work, more rovers can be combined, like Snap robot and modularization is expected. Thank you for AirPack members and all staff of ARLISS 2024. Thank you for listening.
Thank you very much for your presentation. And the next team is Tokyo University of Science, SHIKOU. This is the last team of first half team. Please prepare for your presentation.
Can you hear me?
Yes, I can hear you.
Okay. Thank you. Okay, let's start our presentation. We are SHIKOU from Tokyo University of Science. I will report our results. First about us, We are a team of 10 fourth-year undergraduate students from the Kimura Laboratory at Tokyo University of Science. Our mission is demonstration and information learning by two rovers, and the background is exploration of the environment around man activity bases on Mars. Objective is to provide a more accurate search than conventional multiple unit searches in which the positional relationship of multiple units of data is determined by a follow-up driving system. Here is a detail of our mission. It says using multiple small rovers is one of the popular way of exploration. However, one of the problems of this exploration is the complexity of information. To solve the problem, we set the mission to realize follow-up driving system. This slide is about small rovers development. Due to accurate design with 30 CAD ultra-compact circuit with 4 layers board, it is possible to develop two small rovers. It is hard to fit two rovers into the weight and size regulations that originally had to be driven by one. Our software follow-up driving system is synchronized via Bluetooth communication, and rover 1 moves using PID control, while rover 2 moves by detecting the red color of rover 1. This is follow-up driving system movie. At this time, we use yellow as the detection color. Success criteria is as shown in this slide. And mission sequence is as shown in this slide. Okay, I will report about first trial. Result of the first trial is not achieved or minimum success. Because of the disconnection of the secondary CO2 rover's power, the fuse could not be triggered, so separation from the cover wasn't succeeded. VOC rover continued autonomous movement within the cover. This slide shows release sequence data. As you can see, release detection was succeeded. This slide shows that VOC rover's landing sequence data. What I want to emphasize here is that even though there is a momentary power loss due to landing impact, the problem is restarted by the demonization. This was an issue of laboratory phase of the year. This is a progress for level. Next, about second trial. We couldn't achieve the minimum success. Both rovers could not move to the program after the release judgment due to the SSH connection at the time of progress execution. After the completion of the competition, we tested various scenarios and concluded that the issue is likely due to the way the SSH connection is terminated. It depends on whether the command prompt is closed first or if the Wi-Fi disconnects first. The trend from the results of this project are as follows. For example, overall schedule management, pursuit for soft landing, and so on. Finally, thank you for your attention, and we look forward to working with you again next year and beyond. Thank you.
Thank you very much for your presentation. The first half of the teams have finished their presentations, so we will now take a 5-minute break.
Can you show it?
Yes, I can see it.
Thank you. I will present the report from Team NAVi of Tokyo Information Sciences.
Our mission is to achieve high precision guidance using a simple introductory concept. We aim to reach a 0-meter goal using GPS and ultrasonic sensors. Next, I will introduce this concept. We use Python 4 program and build the airframe with a 3D printer. In the first launch, communication was lost at an altitude of 3,139 meters. The parachute did not separate, so we had to stop the mission. We found out that a GPS problem caused the system to stop during the descent. For the second launch, we fixed the GPS issue. The CanSat landed 2.1 kilometers from the goal, and the parachute separated successfully. The CanSat hit large twice, but kept moving forward without any problems. After using GPS to reach close to the goal, the ultrasonic sensor started detection the target. The program ended normally at a distance of 3.8 meters from the goal. Our success criteria as follows. Minimum success, the CanSat must separate from the parachute normally, use GPS to move towards the goal, and travel more than 5 meters. Also, the pressure sensor must work to confirm separation from the carrier. For success, the CanSat must reach the designated area and, considering the GPS accuracy, get within 10 meters of the goal. Extra success, the CanSat must reach the designated area, measure the goal position, and overcome GPS error to achieve a 0-meter goal. The minimum success criteria were achieved by detection release from the carrier, using the pressure sensor, initiating the cutoff, and travel more than 5 meters towards the goal, resulting in success. Full success was achieved by successfully navigation to the designated area and starting the search for the goal, stopping at a distance of 3.0 meters from the goal, resulting in success. Extra success was not achieved because also the goal detection had begun, the 0-meter goal was not reached, resulting in failure. Positive points, the stop routing worked smoothly, and the heavy tires helped prevent the CanSat from getting stuck. Improvements, we would like to expand the designated area and strengthen the stabilizer. In the future, we aim to achieve a 0-meter goal using distance sensor and committee improving our development process. Thank you, AirPub team and ARLISS staff. Thank you for listening.
Thank you for your presentation, Noazak. And the next team is University of Louisiana at Lafayette, Team Blacklock. Please prepare for your presentation. Sorry, Team Blacklock.
Just one moment while we pull up our presentation.
Sorry. One more time, please.
We are working on pulling up our presentation right now.
Oh, okay. If you need more time, I'll move to the next team.
Yes, let's do that. We appreciate it.
Okay. The next team. Keio University, Keio Team Wolve'Z. Please prepare for your presentation.
Okay. Can you see it?
Yes, I can see it.
Yeah, okay. Okay, so now let me start of the presentation of result of ARLISS2024 of Keio Team Wolve'Z. First, we talk about the background and our mission. Our background is Moon Cave, which in Japanese Getsumen Dokutsu. It is suitable for exploration base because the stable temperature, radiation weakening, and the safety from the meteorites. So we propose the slowing as material transportation into the cave from the ground. That is background, and the slow out background, we propose a mission that is the accurate detection and accurate slowing of modules. And look at this photograph of the light. We slow the two modules one by one. First, we slow the first module, which is called receiver module, and after that, we slow the second module, which is called supplies module, to the first module precisely. That is our mission. And next, we talk about the mission flow. Minimum success is a rotating mechanism test run, and the middle success is slowing the receiver module, and the full success is slowing the supplies module to the first module. And advanced success is a goal tracking. That is our mission flow. And next, we talk about the structure details from the hardware and the software of each viewpoint. These are our originality of the airframe. From the hardware viewpoint of 2 points. First point is receiver and the supplies modules. These modules are pasted AL markers, both like these photographs, and it's launched by burnout and the springs. Look at the movies. This one and the light. Yeah, these are our launch. These are our slowing, sorry. And the next point is a slowing stance. We have the slowing stance for the slowing, and it is made a rotational mechanism with gears like this. It needs a perfect gear engagement, so it is so hard to adjustment of the gear. And next one is from the software. The software from the viewpoint have the 3 points. The first point is the landing judge. We have the multiple sensors on the airframe, like acceleration and time and pressure. Thanks to it, CanSat can operate normally even if one sensor is broken. And second is a recognition of module and goal. We have the 2 systems for detecting modules. First is a color recognition and AL markers. Color recognition applied to the power separation and goal tracking, so these are very important for our mission. And the third point is a routing plan. CanSat have to go to a slowing position that is a 60 centimeter from the receiver, so we have to make the original routing plan for the slowing. So we separate the plan from the far or from the receiver, less than 6 centimeter or more than 6 centimeter. These are our structure details and originality for the airframe. So next, talk about the result of our launch. We launched twice, and so I'll explain one by one. Our first launch was the result is minimum success.
because unable to drive due to a tire separation. Look at the photograph, and completely our tire is broken. Maybe the cause is a landing impact. We think the CanSat failed this angle, like estimated landing site map. So all the impact on the tires, so our tire is completely broken. So the improvement, we think that review of test and rain cushion of the end of the tires. That is our first launch. Second launch is the result was a minimum success due to a failure to burn out in the separation seat. The cause is, we think, the overburn resistance, so resistance will be ineffective. So improvement is the other method of escape. That is our result. So last, I wrap up this presentation. Both of results are minimum success, and we found technical issues and some management issues. So next year, we employed a new system and achieved mission completely. And we got some lessons from ARLISS2024. So take advantage of this year's achievement. We get the next year's objective completely. So that's it. And to authorize people to ARLISS2024, thank you very much for your effort in organizing the competition. That's it. Thank you for listening.
Thank you very much for your presentation. And the next team, the University of Tokyo Flying Cactus. Please prepare for your presentation.
Sure. Can you see the slide?
Yes, I can see.
Okay, so let's start our mission report from Flying Cactus. This is our sequence diagram of missions. So we fly back by multicopter to achieve the goal. We built two types of multicopters. The left one is handmade plane with a 3D printer and carbon rods. The right side is carbon material airplane sponsored by Sankyo Manufacturing Company. This is a description of the aircraft. The part written in the red is newly introduced or originally created. This is about the performance of the aircraft. The weight of the aircraft is really light, and this enables the aircraft to use large battery. With a large LiPo battery, the theoretical range is 7.5 kilometers when flying at 5 meters per second. Our concept for the aircraft was to have as much range as possible. To ensure range, we used CFRP and titanium in the fuselage and large foldable propeller. Also, vibration countermeasures were very important, so we made some original vibration reducer to reduce the influence to the flight controller and use nylon nuts to prevent parts from falling off. The circuit had three major innovations: high reliability, lightweight, and big battery. High reliability, lightweight, for high reliability, improve the circuit design with creative solutions. And in addition, we choose
compact size of the component like these pictures. Moreover, our big battery enables extended the cruising range of the vehicle. For control, there were three main development concepts: stability, simplicity, and high accuracy. We set up in the event of the error, so the loop processing does not stop when an error occurs. In addition, a high-speed image recognition model of 0.2 seconds per image was realized. This image recognition accuracy exceeded 95%, like this, achieved highly accurate flight and landing. Here are the results of this event. The first challenge was retired because of the landing mechanism did not work properly and the flight became impossible. And the second challenge is the landing mechanism worked properly, but the flight instruction was not passed and the flight did not start, so the aircraft was retired. Thank you for listening and the ARLISS management. Thank you.
Thank you very much for your presentation. Okay.
Team BlackRock is prepared to go now, if y'all want to slot us in.
Oh, Team BlackRock, are you ready for presentation?
We are.
Okay. Can you share your slide?
Can y'all see this?
Yes.
Perfect.
All right, I'm going to go ahead and start if everybody's ready. Hey, y'all, we're from the University of Louisiana at Lafayette. We are Team BlackRock, and this is our presentation for the ARLISS 2024 competition.
All right, we're mechanical engineering students from Lafayette, Louisiana in America. We competed in the ARLISS project as our senior project. And we started from scratch in design and built our CanSat in 15 weeks from the ground up on a very limited budget. As for the design, we decided on a two-wheel design using tape measures as stabilization and balancing. Our CanSat consisted of an aluminum frame, and we 3D printed parts from ABS to house all the electrical components. The wheels are also 3D printed from ABS, and polyurethane was bonded to the wheel to act like a tire on the wheel. And these wheels actually perform very well on the desert terrain.
As for our coding logic and strategy, firstly, any movement of our motors and any navigation does not begin until it reaches a certain altitude. Once it reaches that certain altitude, which it does during the ascent of the rocket, it now has to recognize if it's below a certain altitude on the descent of the CanSat. And once it's below that altitude, the motors will start rolling forward. And the strategy behind that was to, upon landing, the parachute would end up falling behind, which makes it a lot easier to release our parachute so we don't get tangled in it as well. Then once the CanSat lands on the ground, it is then the parachute is then released, and that's when the navigation code begins, in which the CanSat orientates towards our destination, and then moves forward for a certain amount of time. And that process basically repeats until it's 5 meters away from our final destination.
So for our results, we performed 2 launches, and with both launches, the robot found a way to get tangled, the parachute found a way to get tangled up in the motors. So our first launch, the CanSat was found 2.8 miles away, and the parachute was tangled in the motor. However, the CanSat was still 100% functional, although the launch was unsuccessful. And for the second launch, the CanSat was found 6.5 miles away. The parachute again was tangled in the motors, and the power wire was cut. So the CanSat was not functional and the launch was unsuccessful.
So now I'm going to go over some of the lessons we learned through this experience. The first thing was that our CanSat almost exceeded the maximum diameter size. We had to make some last minute modifications in the field. And looking back on some of the other teams' designs, we got inspiration from the outer shell that many teams used to ensure that their CanSat fit in the dimensions properly. We also realized that more engineering is necessary to prevent the robot from getting tangled in the parachute. One of the limitations we faced is we weren't able to do a full-scale launch test from a simulated rocket canister. And we're working with different teams of engineering students here on our university campus to build out testing apparatus for future teams. We also realized it would be beneficial to have a higher battery capacity. We allocated about 2 kilometers of driving distance for our CanSat. And after launching the robot several times, we realized that it is not uncommon for the robot, the CanSat, to travel much further than 2 kilometers. So that is one specification we are going to review for future years and encourage future teams to design higher capacity batteries. I just want to close with a word of thanks to all of the ARLISS staff and of course the AeroPack for hosting us on this amazing experience. That concludes our presentation. Thank you all.
Thank you very much for your presentation. Okay, the next team is Institute of Science Tokyo, Lastech. Please prepare for your presentation.
Okay, my name is Rintaro Yamamoto. On behalf of Team Lastech from Institute of Science Tokyo, I'll explain our mission. First, about the background, wide area exploration is important in the search for life on other planets, but it's difficult with the large, versatile rovers currently in use. We believe by focusing on specific function and using a parametric reaction, we could miniaturize the rover, making it possible to deploy in large numbers and conduct wide area exploration. So we anticipate a mission using small rovers to explore wide areas. And our CanSat mission is demonstration of a small rover enabling on-site amino acid analysis over wide areas where large rovers face challenges. This is an overview of our CanSat. Our CanSat can be divided into 2 parts, the left side and right side. Left side consists of the electronic components, blower, air duct, and sample guide path. The blower and air duct on the left side lift surface particles and collect sample by sample guide path. The right side consists of the needles, sample storage, camera, and LED. The sample storage is divided into 2 parts by thin film, and powder and water stored separately. The needle controlled by a motor moved up and down to break the thin film, allowing the powder and water to mix as well as collected sample and reagent. The camera captures the color change. For our mission, the soil in the Black Rock Desert is alkaline, so we used dried purple cabbage powder to simulate the detection through a parametric reaction. Next, I'll explain the specific mission sequence. After the parachute deploys and the CanSat lands, the first photo is taken to capture the original color of the water. Next phase, the needles breaks these thin films to mix the powder and water to prepare the reagent. After that, the blower collects the samples, and by moving the needles up and down again, the sample is mixed with the reagent. Finally, color codes are extracted from the 3 captured images and transmitted. I'll discuss the results. In the first launch, the CanSat was hit hard due to the strong winds, so we could not continue the mission after land. In the second launch, the CanSat landed successfully, and we are able to achieve the objective outlined in the slide. However, upon landing, the cable connecting the camera came loose, so we are unable to capture images, extract color code, and transmit them. We conducted an additional experiment after the mission. Based on calculations that took into account water evaporation, we determined that the amount of the sample collected was 38 milligrams. Then we conducted an experiment using soils collected from the Black Rock Desert, observing the colorimetric reaction with 10 milligram, 20 milligram, and 30 milligram samples. These photos show the result of this experiment. From this experiment, we confirmed that the amount of the sample collected during the mission was sufficient. This is the achievement evaporation according to the success criteria. From additional experiments, since we did not use Black Rock Desert soil when setting this success criteria, we think it's inappropriate. This item is not achieved according to the success criteria, but we believe it's effectively achieved since we could collect a sufficient amount for the reaction. This is our conclusion. Thank you for listening.
Thank you very much for your presentation, Lastech. And the next team is Shizuoka University SATT ZEAL. Please prepare for your presentation.
Okay.
Sorry, are you speaking now?
Sorry. Can you hear me?
Yes, I can hear.
Thank you.
Are you ready for presentation?
Wait a moment, please. Sorry.
Okay. そうですね、日本語で失礼します。
はい。
今、なんか作業で困ってたりしますか？
あ、ごめんなさい、大丈夫です。始めます。
お願いします。
はい。This is G of Shizuoka University SATT. We are going to start our presentation now. First of all, I introduce about our mission. The main mission is developing a console with an autonomous deployable structure based on Jackson Q and use a magnetic field resonance coupling WPT with a pair of FPC coil to light up LED. Submission is demonstrating self-made crawler mechanism. Next, I introduce the details of our concept. Jackson Cube is a kind of cylindrical spiral origami. It expands from a plate to a cube. In this project, we use modular, cubic, deployable structures inspired by Jackson Cube. This is a detail of it. To achieve our mission, we attached FPC coils on the side of this structure. This video is expanding of a modular cubic deployable structure. Although the structure originally has two stable states, it is made to be stable only in the deployed state, allowing it to deploy autonomously and maintain the deployed state. Using the cubic structure, we demonstrate wireless power transmission with magnetic field resonance coupling. This coupling method uses two coils with same resonance frequency. First, pass AC current at resonance frequency through the transmit coil. Then, magnetic and electrical resonance state are achieved and AC current with same frequency flows through the receiving coil. This method has high efficiency and long transmission distance. The crawler mechanism increases the ground contact area compared to normal wheels and improves the running performance on soft ground. This is as seen from a running test at Nakatajima Sand Dune. It showed better running performance than our two-wheeled concept. The results are as follows. We launched once. We found the broken concept and were able to confirm that the parachute separation and the deployment of the concept was successful. My PC is freezing.
Oh. Ah, okay.
The control log revealed that the landing decision was made at an altitude of 500 meters. As a result, the CanSat has inflated its parachute and deployed itself at an altitude of 500 meters, and then failed due to the impact of free fall. So we achieved the success criteria from 1 to 3.
Sorry, time is up, so please be quick.
Okay. On the other hand, it was impossible to achieve more. Lastly, thank you for supporting our challenge and giving us the best opportunity. Thank you for listening.
Thank you very much for your presentation there. Okay, and the next team is the University of Tokyo, Corvus. Please prepare for your presentation.
Sure. Do you see our slide?
Yes.
Okay. I'd like to start our presentation of Corvus, the University of Tokyo. Our mission overview is try to achieve 0-meter flyback by multicopter, as no one could achieve before the ARLISS. And here's our mission sequence from 1 to 7. I separate 1 to 5 in the minimum criteria, and 6 and 7 is full criteria, and extra criteria is other things. And this is our concept, and the characteristic is flyback by this drone, this part. And here's a stand-up mechanism in the below of the concept. It is needed to stand up the drone. This is because drone cannot fly without looking upwards, and achieving a goal come with GPS and image recognition. And with this is a photo propeller. This allows the CanSat to set his balance and lower to easy stand up. And this is the CanSat with in cases, and this is picture. And this is a stand-up mechanism video. Like this video, the stand-up mechanism allow drone looking upwards. And this is a second time video. Okay. And here's the result. The first attempt, the parachute and envelope, the plastic case are destroyed in free fall. And second attempt, the drones and the CanSat successfully opened parachute and landed and deployed and took off. But drone crash landing with 326 meters remaining. This is our first launch result. Everything is worked in the free fall. The constructions are broken down, and fortunately the electric components were still alive, so we can use and fix it. And this is a parachute, and this is a envelope in the case. So we underestimated the opening impact, and this caused parachute broken. And this is the second launch result. As I mentioned before, the drone unexpected landed in the desert, and he flew 4.71 kilometers, and the battery deployed from Earth. And from the flight review, there was discontinuation changes in the altitude measurement inside the Pixwalk. The Pixwalk is a flight controller in the drone, and this is not a machine we made. And maybe this possibly due to the misestimation of the height and cause unexpected landing. And this is a flight video. Here's a drone. At this time, the drone perfectly flight, but after that he broken down. And here's our success criteria. At the second launch, we perfectly get a minimum success, and in terms of the first success, this is not a constant altitude, so this is not good. But here's that I can achieve in the first success, and here's we did not achieve this criteria. And for the reflections, we don't have any inadequate provision of one-ton parts like propellers and other electronic things, and we hadn't tried to a long distance straight flight. This is not we cannot do in Japan, so we have to do this in the desert, but because of the bad weather or other things, we cannot do this before the launch. And here's acknowledgement. Thank you for ARLISS management teams and Airpact and all those involved in the development. Thank you for your attentions. Thank you very much.
Thank you very much for your presentation. Okay, and the next team is University of Tsukuba, STEP. Please prepare for your presentation. Team STEP.
Yeah,
okay.
oh, sorry. Can you hear me?
Yes, I can hear.
Okay. Good morning, everyone. Today, I will present our work at the University of Tsukuba, STEP. Let me start by introducing our CanSat. It's called Dunamis, and we participated in the comeback mission. Our CanSat has two main features. First, it is equipped with expandable tires. These tires expand by 40% during deployment, which improve its ability to navigate rough terrain. Second, its modular design allows for easy disassembly, making maintenance simpler and more efficient. Now, I will discuss the competition result. In the first launch, a higher than expected force was applied by accident during deployment from the rocket, causing the CanSat to detach from the capsule. As a result, it fell freely and could not function, leading to its retirement from the competition. During the second launch, the burn-off registers connector detached due to the impact when the parachute deployed. This failure prevented the capsule from opening, causing the CanSat to retire once again. We believe these issues stemmed from insufficient structural strength. The connector was vulnerable under load, while we had prioritized ease of maintenance.
This compromise made it difficult to ensure the necessary durability. Moving forward, we aim to redesign the crucial components to be more robust without requiring frequent replacement, ensuring better performance in future missions. Thank you.
Thank you very much for your presentation. Okay, and next team is Costume Cockrus from Costa Rica.
Okay, I'm going to start sharing. Can you see my screen? Okay, well, hello, I'm Fernanda. I'm a member of the Cockrus team from the University of Costa Rica, as already mentioned. And I'm going to talk about our project, Roberto. And well, we participated in the competition as a comeback. Our rover was quite basic in terms of structure. The chassis was made from aluminum, which we selected due to its lightweight and strength. But the wheels, the third support, rims, and the base for the PCB were all 3D printed using TPU and PETG. These materials were chosen because TPU provided flexibility, allowing the wheels to absorb some of the impact during the landing, while the PETG offered higher structural integrity. Additionally, we designed a protective casing. This casing was also custom manufactured by our team, and as you can see on screen. In terms of electronics, our rover was equipped with several sensors, including a GPS, accelerometer, gyroscope, magnetometer, and an encoder for each wheel. Our mission beyond developing the electronics and structure was to achieve that first flight heritage, essentially proving that our satellite-type rover could survive the harsh condition of the launch, descent, and landing. Now, in terms of results, we conducted 2 launches during the competition. In the first launch, our rover experienced free fall, and unfortunately, its structure didn't survive the impact. However, the PCB did survive and continued to function, which was a small victory in itself. After this, we identified areas for improvement in the programming and design for the second attempt. In the second launch, the descent was mostly successful, as it wasn't a free fall this time. However, several factors such as the landing position, which was sideways, and issues related to the release system prevented us from fully continuing with the mission. So, yeah. Among the lessons learned, there are several I would like to highlight. Firstly, well, we were able to implement our engineering knowledge in a real-world scenario, facing unpredictable conditions like the desert environment. We also discover like new materials like carbon fiber composites that we can implement for a future project to improve the weight to strength ratio of our rover. These materials will offer like better resistance to high impacts that is crucial for this type of launches. Also, this experience taught us that in projects like this, having like critical system with redundancy is essential to ensure that one failure doesn't mean mission failure. We also learned a lot about problem solving. Many issues arose throughout the development and testing phases, and we had to troubleshoot on the spot, often with limited resources, mostly in the desert. This helped us sharpen our problem solving skills. As well, we learn how to work effectively as a team under pressure. Soft skills like teamwork and communication skills were greatly enhanced, and we had to constantly coordinate between different teams like the mechanical, electrical, and programming, and ensure that we were all working towards the same goal. Being able to communicate effectively, especially when our problems arose, was key to keeping the project on track. And finally, one of the biggest takeaways is that the dedication and persistence really do pay off. We faced many challenges along the way, but through all of this, we stay focused and kept pushing forward. In the end, we managed to accomplish much more than we had initially thought was possible, and that in itself is a reward. So yeah, thank you so much for your attention.
Thank you very much for your presentation. Okay, Team Cosmics, are you here? Are you ready for presentation? Okay, I think they are not participating in this meeting, so I'll skip their presentation. Okay, all participating teams have now completed their presentation. Next, the management members will make their presentation. The first is Mr. Yoshida. Please go ahead. Mr. Yoshida, are you ready? Oh, okay.
I'm sorry, can you hear me?
Yes, I can hear you.
Can everybody see this screen? Can everybody see this screen?
Yes.
Okay, I'll start. Good evening, everyone. I'm Yuto Yoshida from ARLISS management team. At this year's ARLISS, I focused on shooting video to share the event with as many people as possible. As part of this effort, we wanted to obtain videos shot from above, and this is how the project we are introducing today got started. This is UTSAT. First, I'll talk about the feature of the CanSat. It was entered in the CanSat-Class, and it has two cameras to shoot from different angles. It is basically made up of ready-made products because I had to complete it by myself in 1 month. Next, I'll talk about flight logs. The UTSAT was launched twice. The first time, it felt too far away, making it difficult to find, but we succeeded in shooting some very wonderful videos. The second time, a few parachute cords broke on impact, and the CanSat descended while spinning. So unfortunately, it wasn't able to shoot any good video. Thank you for waiting, and ladies and gentlemen, please look at the video. It was able to shoot this ARLISS. The left video is from camera facing horizontally, and the right one is facing downwards. I'm afraid, but due to the limited time available this time, I will speed up the video to 25x. I will upload a long version of this video to the ARLISS account on YouTube. By the way, the digest video for this year has already been uploaded. Have everyone all seen it? Please check it out. Finally, I'd like to express appreciation to David for providing the rocket and everyone at Aeropark. Thank you very much.
Thank you very much for your presentation, Mr. Yoshida. Okay, next is Mr. Kaneko. Please prepare for your presentation.
Yes.
And I will announce for participation. Please vote form before this management team finish their presentation. Please vote your form. Okay.
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 Yes. Hi everyone. I'm Sota from ARLISS management team. Our concept is 5 bundling concept by open classified. First, our concept mounting a camera and a keychain on a 250 milliliter can to take image from the air. It is smaller than 350 milliliter CanSat-Class. So we launched the 5 CanSat and at a single open classified. Next, this is a video we are take. Here is we also took a we also took a picture of a keychain in front of camera. The first one is the ARLISS logo. This logo is made by Yuto Yoshida in management team, and the second one is TDU logo. Prof. Hattori provide this keychain. The third is active child. He is supporters of the crowdfunding campaign we conducted for ARLISS. The fourth is Clear Usui. She is a rocket idol VTuber who helped us promote or crowdsourcing campaign. And an additional camera was installed to record video. So beautiful area video was also taken. That's all. So thank you for Jonathan and ARLISS LPAC, all members. Thank you.
Thank you very much for your presentation and a very, very beautiful video. Okay, next program is I'll share my slides. The next program is remarks from UNISEC faculty. We will receive from Professor Inamori. Professor Inamori, are you here?
Thank you very much. Sorry, so my camera doesn't work. So, okay. Okay, remarks, right? And thank you very much for all students, all attendees to make this very interesting presentations. And I'm truly delighted to see many new ideas and the challenges in this year's ARLISS. And the students achieved remarkable results with their concepts. So it's very interesting. And of course, not everything may have gone exactly as planned. But in such cases, careful reflections, lessons learned are very important. So based on today's presentations, and maybe after the presentation, maybe in the group, in the team, you may have some discussions. So please continue pushing your analysis further, and the next concept and lessons learned is very important. And so this by, how can I say, comments, but okay, so maybe I should say that, so to the AeroPark members, thank you very much for giving us such a great opportunity to ARLISS every year. And thank you very much. ありがとうございます. And I share that there were no big troubles during ARLISS, and thank you members for all your efforts.
Thank you very much for very nice comment, Professor Inamori. Okay. Next, we will now take a 15 minutes break. And during this time, we will decide on the awards. And UNISEC faculty members, please join in the breakout room. And the name is UNISEC Kyoin, as we decide the UNISEC awards. Okay. We will announce the awards now. So, Mr. Matsuhashi, please go ahead.
Can you hear me?
Yes.
Yes, okay. Let's move on to the award section. First, we provide accuracy award. This is based on the distance from the goal marker. I want drum roll from Mr. Okada. Wait, just a second. Third prize is given to Team Corvus from the University of Tokyo, Congratulations. Next, second place is given to
them.
Noah's Ark from Tokyo University of Information Sciences. Congratulations. Next up, first place. This prize is given to
then
Nix OverLights from Niigata University. This team achieved 0 meter from the goal, despite being a first-time entry. Congratulations. Actually, we have the accuracy award for non-student entry. This award is given to
them.
Supernova from Tokyo University of Information Sciences. This team has also achieved the 0 meter goal. Congratulations. Let's move on to the best mission award. There are two teams tied for second place. Second place is given to
them.
Flying Cactus from the University of Tokyo. And Step from the from University of Tsukuba. Congratulations. Next, first prize of Best Mission Award. First prize is given to
then
TMU NAVi from Tokyo Metropolitan University. Congratulations. This is a technical system award based on the technical novelty and difficulty of the system. Third prize is given to
them.
TMU Super Spider Liner. Congratulations. Actually, there are two teams tied for first place of Technical System Award. First prize is given to
them.
Flying Cactus from the University of Tokyo. And another team is TMU NAVi from Tokyo Metropolitan University. Congratulations. This award is the overall winner of Mission and Technical Systems Award. The overall winner of ARLISS 2024 is
them.
TMU NAVi. Congratulations. You are the best in ARLISS 2024. We plan give Challenger Award for the team challenged new goal, but this year there were no recipients. This is UNISEC Award. UNISEC Award is given by UNISEC Faculty. Could you explain this award, Professor Nakanishi?
Okay, so the UNISEC Award is given for challenging mission, but unfortunately they didn't got any successes, and so except of any other winner, the this is the given by the selected from the UNISEC faculties. So the UNISEC award is drum roll start. Okay.
Then
the team Last Highball from the University of Electro-communications. So congratulations. So their mission is very challenging. For example, the connecting and the release in the running mission. So that is very essential for the future rover mission and very challenging. The technology is very nice. So the selecting the UNISEC award is very difficult for us because this year is also there are many technology challenging the technology significance mission. Finally, we chose the Last Highball. So congratulations.
Thank you, Professor Nakanishi. This is end of our section. I will share this presentation slide later.
Thank you very much. Thank you very much, Mr. Matsuhashi and Professor Nakanishi. And congratulations, TMU, NAVi, and the other team. This is the end of all of the events of ARLISS 2024. We are happy to see so many great results and really exciting. Thank you for participating in ARLISS. We look forward to seeing you again next year at Blackrock. Thank you so much.
Thank you so much.
Thank you.
Congratulations.
Thank you.
Thank you.
Thank you.
Thank you. Congratulations.